All right, let's get started, you guys. Um, uh, Number one, uh, I posted the first homework for you on the Blackboard. Um, I attempted to set it up in a way so that you can download the assignment and then you can upload your answers. Bear in mind, this is the first time I've done it. Okay, so you guys are kind of my guinea pigs. And so if you have any trouble downloading it, please let me know as soon as possible, and then I can send it to you in another way. And if you have any trouble with uploading your answers, I don't know, see if you can figure it out. But if you can't, then just send it to me by email, and that'll be just fine also. It would be nice if you could make your answers into a PDF that's sort of easy to read. If you have a scanner, that's great. Please use that. If you don't have a scanner, you can certainly take pictures of it with your smartphone. There are apps that are meant to be improvements on just taking pictures, right? There are apps that actually try to transform the picture that's taken at some angle so that your page looks like a rectangle and the background looks like white paper, and then it's easier for me to read. Okay, so see if you can do me a favor and use one of those apps. And if you have any trouble with the techie stuff, by all means, just let me know and we can try to work it out. Okay, that is point number one. Okay, point number two. Did any of you manage to figure out my blunder from the class last time?
I started it and I got in the right direction. I got about halfway through it and I thought I made a writing mistake. And so I went and checked online to see the notes again and saw that you already fixed it. But I was on the right track.
Oh, good. I'm so glad. I totally believe you. And I made a writing mistake. Okay. And so here, I'll just share the iPad with you. Here, okay, you see this, right? And so this was my my whiteboard from Wednesday, and you could see that when I copied things from one page to another, I just forgot the factor of 2 in the denominator there. And that is the downside of just copying things from one page to another, is I have to kind of remember. And so I figured out an improved way. I'll show you. But anyway, because I fixed that factor of 2, and now that propagates through, and it gets to this place, and then down here, it gets to this equation where the factor of 2 is fixed, and now we can move on. Okay, so now that I have sufficiently embarrassed myself, what I've learned is that rather than trying to remember this equation and copy it into my next page, I will copy and paste it with the app. So there's a nice system where I can lasso it. Let's see if this works. And then I say copy. Okay. And then I'll go into my new page and I say paste. Ooh, that's so cool. All right, so now suppose we want to work with this improved equation. Ooh, if it's too big, can I make it smaller? Huh, I can turn it. Wow, that's great. All right, so this is the old equation from last time, now with the correction. So what can we do with that? Okay. So remember what we're trying to do here, right? That our goal is to calculate the magnetic order parameter. That is, when you have a phase, the ferromagnetic phase, so that there's a little bit of magnetic order, how much magnetic order will there be? And it's going to depend on temperature. So we want to make a prediction for how much order there's going to be, this M of T. Right? And we cannot do that in general. There's no simple algebraic solution of the equation, but we can do it as an approximation when M is much less than 1. That is, when there's only a little bit of magnetic order. So what do we get, right? Well, let's take this corrected equation and rewrite it a little bit. So here, this could be written as M is plus or minus the square root of JQ over Boltzmann's constant minus temperature, all divided by temperature. Oh, and let's put the factor of 3 in the numerator like that. Okay. Now, this combination right here, that is the critical temperature that we calculated on Wednesday. Right? So this expression then is equal to plus or minus the square root of 3 Tc minus T divided by T. So this now tells us something that's a little bit interesting. Okay, it tells us that when the temperature is equal to the critical temperature, M is going to be equal to 0. Okay, and when the temperature is a little bit less than the critical temperature, M is going to be a positive or negative number, which is a little bit different from 0. Okay? So M is increasing proportional to this square root. Okay? So because of that, when we say our approximation works for M much less than 1, that means for a small value of Tc minus T. So for Tc minus T to be very small. How small? Well, much less than Tc. So then this quantity is, it's that square root, or we could say it's approximately plus or minus 3 Tc minus T divided by Tc. So we can make a plot of this, right? So we could make a plot that says, suppose you want M of T, and Tc is there. For all the temperatures above Tc, we have just M equals 0. Right? That is the minimum value of the free energy. Right? But when T is less than Tc, then M follows this square root law. So the plot of the square root looks like this, right? It's like a parabola on its side. Right? So you can see that M is increasing away from 0 as T goes below TC. This equation is a good approximation when T is close to TC. When T gets farther from TC, it's not such a good approximation. Then we have to do something different, like solving the equation numerically. I'll show you that in just a minute. All right. Now, this trend for how M approaches 0 when T approaches TC, this is a characteristic behavior, right? And this thing is called a scaling relation. That is, how does M scale with temperature close to the critical temperature? Okay. It is often written as a power law like this, right? To say that M is proportional to Tc minus T to the beta power. And so you can see from this calculation that we are finding that beta is equal to a half in mean field theory. So, this is making a specific prediction that somebody could go and test in the lab, right? Somebody could go measure the magnetic order parameter in some ferromagnet as he cools it through the transition from paramagnet to ferromagnet, okay? And then see what's the trend for how M increases as a function of reducing temperature. Okay? And so here we're making a prediction based on mean field theory that the exponent should be 1/2. Now, this sort of thing has actually been tested in lots of experiments. And it's been calculated in improved theories also. And so I can tell you the results from improved theories. Those show that beta is equal to 1/8 in 2 dimensions, and beta is about 0.31 in 3 dimensions. Okay, so yeah, mean field theory is an approximation. There are improvements that people can make. And this exponent is one thing that people can calculate and compare with experiments, and it's a characteristic prediction and experimentally measurable thing. And this is one example of what is called a critical exponent. That is to say, the behavior near the critical point, near the critical temperature, Tc, is characterized by a set of exponents. And now I've shown you one example, right? That the beta is one exponent that describes what happens close to this special point. And so we get some information about it from mean field theory, and there are improvements that people can do that's better than that. But mean field theory is a good start. It certainly shows us that there is a critical point and that there are exponents that describe what happens there.
Question.
Question.
I'm wondering what decides the value of this critical exponent? What is the physical region of this kind of?
What's the physical reason? Why is it 1/2?
What is the physical origin for this scaling relation?
The origin of this relation.
Yeah.
That's an interesting question, which I'm going to postpone. Okay, I'm going to postpone it because here we see that it comes from, you know, the mean field theory that I set up for the magnet, but later on I'll show you a similar thing that happens in the phase diagram for a gas and a liquid, right? And then when I get into Landau theory, I'll talk about some other more general considerations. So it's a great question, but just hold it for a couple of weeks.
Okay. Thank you.
Other questions about this? Yeah. Okay, well, so far I have shown you what happens when there's, well, first I showed you when there's no interactions, but there's a magnetic field. And now I showed you what if there are interactions, but there's no magnetic field. Okay, so you might be wondering, what if you have both interactions and a magnetic field? Okay. So let's go back to Mathematica to look at that. Okay. So I'm going to stop this sharing and I will start the sharing. Where's my sharing command? I will start the sharing with Mathematica. Okay, so here is the calculation that you looked at before, right? You see the Mathematica on the screen, right? Okay, okay. So this now is a way to check what happens to the plot of free energy versus magnetic order parameter when you have both the interaction term and the magnetic field term. So here is the interaction term, the free energy. Here is the magnetic field term, and here's the entropy term. Okay. So I have the combination of those things, and now I have two sliders where I can adjust to see the effects of both interactions and magnetic field. So when we're at a high temperature, means JQ over KT is really small. There, it's equal to 0. Okay? And the magnetic field is 0. Right? Here, this is just the entropic part of the free energy, which looks like a parabola. Right? And the minimum here is at m equals 0. Now, if I vary the magnetic field, you can see that the minimum shifts over to positive m or to negative m, right? That's what I showed you already for the non-interacting Ising model. Now, what if we go back to zero field? If I reduce the interaction strength or increase the temperature, here we see this splitting, right, of the single minimum into two minima. Right? Now, if I also have a magnetic field, you can see that shifts things from one side to the other side. Okay? So that now, you have these two possible minima, and as you vary the magnetic field, one is lower or the other one is lower. Okay? And we can track which one is the lowest of these two, right? And so at any value of the magnetic field and the temperature, we can say, oh, the minimum is over here, and then gradually increase the field and say, oh, no, the minimum just jumped, now it's over here. Okay? So as a function of magnetic field, there is now a jump in the magnetic order parameter, right? When you change the field, when it passes through zero, the minimum jumps from here over to there and vice versa. So now we could do some numerical calculations to find where is the minimum. Okay, so for any particular input field and input temperature, I can tell Mathematica, go calculate the minimum, right? And so I've done some examples here. First of all, these are plots that show the magnetic order parameter as a function of temperature for different values of the field. So let's look at the middle plot first, the one right here. Okay? This is what happens when the magnetic field is equal to zero. Okay? So in this case, as you cool down, reducing the temperature, the order parameter m is zero until you hit Tc. Okay? And when you hit Tc, it bifurcates, right? It becomes either positive or negative. So right here, this is where the plot looks like a square root law, right? It looks like the parabola on its side, right? So close to the critical temperature, you can see the square root law that I calculated on the whiteboard a few minutes ago. Now, what if you keep reducing the temperature? Well, the positive solution goes around here and it saturates at m equals 1. Right? M equals 1 is the biggest possible value of the magnetic order parameter. You can't have more than 100% order. Or the negative solution comes down around there and it saturates at -1. It can't be any lower than -1 because that's 100% order in the down direction. So this plot is approximately a square root law. It's not exactly a square root law because a square root law wouldn't saturate like that. A square root law would just keep going and getting more positive or more negative. So it's approximately a square root law near Tc, and away, it saturates. It goes to the maximum value of ±1. Okay, that is the solution when there's zero field. Okay? What if there's a positive field? Well, if there is a positive field, then at any high temperature, there's going to be a a little bit of order. Right? And we could see that from a plot like this one, right? Even at a high temperature, if you have a little bit of an applied magnetic field, then you get a little bit of order. As you reduce the temperature, the minimum shifts to be more and more order. Right? That is what's plotted here, right? As you reduce the temperature, the minimum shifts to be more and more order. And then it goes up to +1. That's the maximum possible value. So you can see in this plot, there is no spontaneous symmetry breaking, right? The spontaneous symmetry breaking only occurs if there's a symmetry to begin with, that is, if there's zero field. If you have a field on all the time, then the symmetry is pre-broken, right? And so, it doesn't break, right? Instead, you just have a magnetic order parameter that varies continuously. Now, what if the field is negative, right? Well, then it just goes the other way, right? So if the field is negative, then at high temperature, you have a little bit of negative magnetic order. And as the temperature decreases, you get more and more negative magnetic order. So this is the plot for negative field. Here's the plot for zero field. With zero field, you can go positive or negative. Either way, it's random. And then for positive field, you only get magnetic order in the positive direction.
Question.
Please.
For both of those graphs, TC versus M, I may have missed it. What is the significance of this inflection point here where the curve's really flat and then it sharpens and goes up or goes down, right?
So
yeah, right there.
Here, right? Okay, great point. When you have just a really small field, then you almost have a phase transition there, right? So, when the field is zero, you get a phase transition. You get real sharp behavior, right? The slope of this plot, the derivative, is discontinuous, right? That is, the magnetic order parameter is continuous, but the derivative is discontinuous. It goes from zero derivative to infinite derivative right there. If you have just a little bit of magnetic field, then you almost have a phase transition, right? That is, that the magnetic order responds really sharply, not infinitely sharply, but very sharply, right? So it's almost flat, and then it's almost vertical there. That's the point of inflection that you're noticing. So when there's a little bit of a magnetic field, the curve is smeared out a little bit. Okay? If there's a big magnetic field, then the curve is smeared out a lot, right? And then you just get something that gradually increases, and it doesn't show much of a change near the temperature TC. Okay? So yes, that's what you're noticing, right? Is how a small field gives a small smearing of this effect, and a big field gives a big smearing of this effect. Now, let me show you another way to see the same sort of thing. Okay? Suppose you make plots of M as a function of H for fixed temperature. So here, this first plot, this is a plot for a temperature that's high, above the critical temperature, okay? Here, I'll write that. Whoops, word to text. Temperature, that is T greater than TC, okay? So here, you can see the magnetic order parameter is increasing pretty smoothly as a function of field. Now, what if you reduce the temperature? If you reduce the temperature, the behavior will be sharper and sharper. That is, there will be a bigger and bigger slope right here at the origin. So now I'll mark this curve as at the critical temperature, T equals TC. Right here, there is one point right at the origin with infinite slope. That means the plot is vertical there. Okay? So the slope here is pretty big. If you keep reducing the temperature until you get right to the critical temperature, you get an infinite slope. That is, the magnetization is infinitely sensitive to a tiny little applied field. Okay? So I'll say, notice infinite slope at h equals 0. Now, what if you have a lower temperature? So here, low temperature, T less than TC. Now you have negative order for the negative magnetic field. You have then a jump right at h equals 0, and then you have positive order for positive field. Okay? So this jump, well, people usually call it a discontinuity. That jump is the jump I was showing you over here, right? That if there's a low temperature and you vary the field, it doesn't change much, and then jump, right? It jumps from positive to negative. Or if you take the field going from negative to positive, jumps back. Right? That is the jump that is plotted right there. Okay. And now here is a plot for even lower temperature, T much less than TC. And then you can see there's an even bigger, discontinuity, right? That here, there's a huge jump from negative field to positive field, and hardly any change there and there. Okay? So I'd really like you guys to think about how to go back and forth among these different kinds of plots, right? This is one sort of important lesson to take from the stuff I'm doing this week, right? That is, if you have a free energy plot like this, and the minimum is shifting as a function of field and temperature. And then if you plot out where is the minimum as a function of field and temperature, you get plots that look like this and this. And now one of the homework assignments is to generate your own version of the plots. Plots like this one for zero field and this one for positive field. Now, if you really want to be fancy, you might say, why not make a 3D plot to show how the order varies as a function of both of those things, field and temperature. That's what I've done here. Okay, so here, this is a nice 3D plot that we can look at from different angles. Okay? So here, the vertical axis is how much magnetic order you get. So this horizontal axis is the temperature. This horizontal axis is the magnetic field. Okay? So now you can see the high temperature behavior is like this one. Okay? That is, at high temperature, you go smoothly between negative order and positive order, but then you reach the critical point, and there's a really special point right there, right? At T equals TC and at field equals 0. And that's a special point where this plot splits up into a negative part and a positive part. And there's a discontinuity in between. Right near the critical point, it's a small discontinuity. As you go farther away from the critical point at low temperatures, it's a big discontinuity. So, this is a plot that you can look at from different angles, right? And I can make a physical model of the plot like this, right? It's like a torn piece of paper, okay? And the critical point is like this point right here, the tearing point, right? And so you have smooth behavior above the critical point, you have smooth behavior down at this branch and this branch, but there's a discontinuity in between. And the discontinuity comes to an end right there at the critical point. Okay. Now, suppose we look at this three-dimensional plot from above. Okay. So if we look at it from above, I'm going to make a visualization like this one. Okay. So in this visualization, here is temperature. Here is magnetic field. And we know that M is pointing straight out to us, right? So here, this region is where M is positive, right? Here's where M is negative. This line is where there's a discontinuity, and the discontinuity comes to an end right there. Okay. Let me now make a copy of this on my whiteboard, right? I'll just draw it by hand. Okay. So, stop share. And I'll go back to sharing the iPad. Okay, on the iPad, here is my copy of what we were just looking at. Okay, so here is temperature, there is magnetic field. Okay. And then I'll label this point as TC. So if we plot what we just were looking at, we can see there's a discontinuity all along this line. Okay? So up here, this is where we have the positive order parameter. Right? Down there is where we had the big negative order parameter. Out here is where we have the order parameter equals 0. So this diagram that I'm drawing then is called a phase diagram. So it shows what phase the material is in at all these different fields and temperatures. And now we can label the different things that we've seen so far on this phase diagram. So right along this line at high temperatures, this is where we have the paramagnetic state. Okay? So H is equal to 0 all along this line. Okay? If we apply a little bit of a field up here, we get some small magnetic order that's induced by the field. If we apply a negative field, we get small magnetic order in a negative direction induced by the field. When we go to lower temperatures, right, then we get a state which is ferromagnetic here with spin up, and down there we get a state that is ferromagnetic with spin down. So now we've seen what happens if we vary the temperature, right? If we vary the temperature going straight down like that, then there's a spontaneous symmetry breaking right at this point, right? The system will randomly go to either spin up or spin down. But if we reduce the temperature like that, you'll just be in the spin up state. If we reduce the temperature like that, we'd be in the spin down state. If you vary the field, here, no discontinuity, right? It's a smooth variation as a function of field. If you vary the field like that, there will be a discontinuity when you cross the line between spin down and spin up. Right? It's like crossing the border from one country to another. Things might change suddenly. Right? And then when you vary the field just like that, right at the critical temperature, then that's where you get the infinite derivative. So this is, like a map that shows the different kinds of behavior that can occur. And I'll emphasize the most interesting point here is the point right there, the critical point. So that is at T equals TC and H equals 0. Okay. So that is the most remarkable point on this whole diagram, because that is where the discontinuity comes to an end, right? And instead of having a discontinuous change from spin down to spin up, it changes to a plain old smooth change from spin down to spin up. A couple other terms to tell you about a phase diagram like this one, okay? When you cross from negative to positive fields like that, okay? This change is called a first order phase transition. First order means that there is a discontinuity in the order parameter. In this case, the order parameter is M. By comparison, if you go through the critical point, that is just reducing the temperature like that, right? That is called a second order phase transition, which means that there is, well, I'll say first, it means that the order parameter is continuous. That is, M is 0 on the positive side, and it's, then it changes to being a tiny bit away from 0 when you go to the other side, okay? It smoothly changes away from 0, okay? Well, I won't say smooth, it continuously changes away from 0, but in a non-smooth way. And the derivative of the order parameter, that is dm dt, is discontinuous. Now, the critical exponents tell us information about what happens near the critical point. So near this special point in the phase diagram. We figured out one of those already, okay? So for the critical exponents, one thing that we figured out is that if h equals 0 and t is less than tc, then m is proportional to plus or minus the square root. Well, I won't say it as a square root, I'll say it as a beta power. Plus or minus tc minus t to the beta power. And we found that beta is 1/2. Now, there are other critical exponents which we can also calculate, but to save time, I'll just tell you some of the results, and the calculation is in the book, okay? So there's another critical exponent for the susceptibility. That is how sensitive is M to an applied field. When T is greater than TC. Okay. So that is characterized by the derivative, which people call chi. That is the derivative dm dh, right? Evaluated at h equals 0. Okay, so that is to say, we have a plot of m as a function of h, right? I showed you something like this in Mathematica, right? It's a plot like this, right? And so there is a slope right here, right? A slope that shows how sensitive is M to an applied field, right? If the slope is high, it's really sensitive. If the slope is low, not so sensitive, right? So it turns out that this is proportional to T minus Tc to the negative gamma power. And the prediction of mean field theory is that gamma equals 1. Okay, so that's another prediction. And, it just takes 5 or 10 minutes to derive. And the derivation is on page 22 of the book. Okay, and then a related thing is how does M respond to H right at T equals TC? That is, I showed you a plot in Mathematica that looks like M as a function of H. It's just vertical right there. So what's happening, in this region where it's just vertical at one point? And the result of mean field theory is that M is proportional to H to the 1 over delta power. And mean field theory predicts that delta is 3. So that, it's a cube root, H to the 1/3 power, cube root right around this, this special region. And again, that is derived on page 22. So you can look it up right there. So these are 3 of the critical exponents. There are others also. This is a big field of study that a lot of theoretical and experimental physics research has been done on critical points. And so there's been a huge effort that's gone into it. All right. This is all that I am going to have time to say about the Ising model for now, because it's not a course about magnetism, right? This magnetism was just meant to be an introduction to you for this concept of a phase transition. But really, I want to get into more molecular systems, right? Systems made out of molecules that are flying around and interacting with each other. And so Next week, I'm going to get into the beginning of one of those, which is just the ideal gas. So that's in chapter 3 of the book. So please go and look at that. Okay, I will stop for now, and I hope you all have a good weekend, and I'll stick around to answer any questions. Please.
Could you please go back to your phase diagram page?
Yes. Right here.
I think paramagnetic phase can only exist when H is 0, right? So go beyond the t-axis.
So yeah, you're asking about what's happening right up there, right?
Right.
Or what's happening there. Yeah.
I'm asking about.
I understand the question. I don't have a great answer for the question. Okay, and the point is really it's a question about terminology. It's a question of what to call things. Okay, I think we already see, you know, what's the physical content there, right? The physical state here is a state with a little bit of magnetic order that's induced by the field, right? A little bit of positive magnetic order. And down here is a state with a little bit of negative magnetic order that's induced by the field. Normally, people would still call that a paramagnetic, right? And you know, people would call it paramagnetic, and they would say, "Oh, look here, I have a paramagnet in a field," right? And so they would. That's the vocabulary, right? But that has to do with what words people use, and it has to do with what's a typical experiment, right? You know, in a typical experiment, some guy is, you know, varying the temperature and varying the field, and so, you know, he has a high temperature sample, and he says, "Look, it's a paramagnet." Then he puts on a field, and he says, "Look, it's a paramagnet in a field," right? And so he would label the phase diagram as paramagnet in a field there and there, right? And here he would say paramagnet in no field. From the theoretical point of view, the behavior is just nice and smooth as we go from there to there to there, right? The only place where the behavior is not smooth is right along this line, right? And so when you cross this line, that's where there's a sudden big change.
Right.
And so, and that sudden big change comes to an end at the critical point.
So it seems that there's no way to distinguish paramagnetic phase and ferromagnetic phase if we just look at the phase itself. Because when temperature is higher than the critical temperature and when the magnetic field is non-zero, there is a net magnetization and right, a non-zero magnetization.
Right. So what you're pointing out is, you know, suppose you want to distinguish this point and this point.
Right.
No, those look the same, right? That you can go continuously from one to the other, right? And there's you know, no phase transition there, right? And so people would use the word ferromagnetic down here because they know, you know, what happens if you turn off the field, right? And so they know that if you turn off the field, you would still get magnetic order, right? Mm-hmm. Whereas over here, if you turn off the field, you would not get magnetic order, right? But, you know, if you have no way to turn off the field, right? If the off switch on your magnet is broken, right? So your magnet is stuck on, right? And you have no way to turn off the field. Then you wouldn't be able to tell the difference going along there.
Okay.
All right. And more than that, you could say start here and gradually increase the field, and then gradually reduce, or excuse me, gradually increase the temperature, and then gradually change the field, and then gradually change the temperature again, right? And you could get from there around to there without ever going through a phase transition.
Right.
Right? But if you go this way, you do go through a phase transition, right? And so, that's like my model with the torn piece of paper, right? To go, where did I put my torn piece of, well, I need to turn it on, right? To go from a point like there to a point like there, you could go across the transition, or you could go around the critical point the long way, right? And you get from the same starting point to the same ending point, but one way you cross a phase transition and the other way you don't, right? And so that's why it's good to look at the 3D plots, right? Or at the torn piece of paper, and then you can see the whole range of behavior.
Okay. Thank you.
Good, good. Is there a question from anybody else?
I have a question, and I was formulating that as you were going. So the plot that we saw earlier, the susceptibility plot, the hyperbolic tangent looking plot, chi, I believe it was. So my understanding so far,
one, right?
yes, yeah. So the rate of change of the magnetic order with respect to the magnetic field at 0. So I'm curious. I understand it is regulated by the temperature change, and I think I understand that the temperature change is influenced by the critical exponent and or the interaction parameter JQ over KT. I'm wondering, what is the relationship between the two, i.e., where did the interaction parameter go? Is it only influencing the temperature?
It influences the critical temperature.
Just the critical temperature.
So the critical temperature, this is JQ over Boltzmann's constant. Okay, so suppose J is 0, right? So suppose we go back to the non-interacting Ising model, right? So if J is 0, then TC is 0, right? And then we would say, well, I'll make another page, right? So for the non-interacting, that is J equals 0, so TC is equal to 0, right? And then the susceptibility is proportional to 1 over T, right? So it's not 1 over T minus TC, the TC goes to 0, so it's just 1 over T, right? And that is consistent with the hyperbolic tangent thing that I derived for you several days ago, right? That in that case, we had M is the hyperbolic tangent of H over KT. So dm dH at H equals 0, well, I think it's 1 over KT. Right? And so if I can differentiate hyperbolic tangents in my head. And so, yes, that is consistent with this finding. So if you were to plot what is the susceptibility for, as a function of temperature, right? For the non-interacting model, it goes like that, right? That if this is T equals 0, absolute 0 Kelvin, right? I don't really need this side of the plot, do I? Okay, right. So if this is absolute 0 Kelvin, then, the non-interacting model has a susceptibility that diverges at 0 Kelvin. Right? By comparison, the model with interactions has a susceptibility like this that diverges at TC.
Gotcha.
Okay. It's good.
Yeah, good. Thank you.
Okay. All right. Well, I'm throwing a lot at you all at once, but I would say, the most important thing to get an intuition for is about the different plots and the relationship between them, right? And so, you could look at the plot of the free energy and see how you adjust it if you move the sliders for interaction strength or temperature versus the slider for field. And you can even write down in a lab notebook, right, as if you were doing an experiment, where is the minimum? And then how does the minimum change if you change temperature or if you change field, right? And see how that leads you to plots like the M of T or M of H or the 3D plot of M of T and H. Okay. And the first problem in the homework is supposed to help with that also.